In this video, we're going to discuss complexity analysis and then apply it a little bit to sorting. So, how long does it take to transfer 10 megabytes to a collaborator at UIC? Well, 100 megabytes, etc. Well, here are the different values. Okay, so first we're going to talk about constant time. Constant time means there's always some constant k such that this operation always takes k nanoseconds. A statement takes constant time if it doesn't contain any sort of loop, it doesn't call on a method with an unknown time, or is not a constant. If a statement involves a choice, each of which takes constant time, we consider the statement to take constant time. This is consistent with what's called worst case analysis. So let's consider the following lines and the number of operators. Let's say this is 1, and we'll say this has two operators. We'll say this one has 1 operator. This is 1. This is just syntax 1, and then 3. Print, print, print. So either line 4 or 6 executes. Therefore, the total number of operations is 8. So in this algorithm, the number of operations is fixed. So it's a constant time. In a higher level language, we do not know how long each operation takes. We don't really care though. If x is less than 10 or x is less than or equal to 9, we don't really care. The compiler most certainly optimizes this. In a high level language, we cannot do an exact analysis. Our timing analysis will use major oversimplifications. We can still get very useful results. We may not be able to program to predict to the nanosecond how long it will take, but we do know some things. This loop takes k times n plus c for some constants k and c. K is how long it takes to go through the loop once. The time for j equals j times I to execute, plus any loop overhead. N is the number of times, and c is the initialization time. So the total time, k times n plus c, is linear in n, meaning it's based on n. So again, let's take another example. This is 1, this is 1, this is 1. This is 2 operations, and this is 2 operations, and this is 1. So we've got 1, 2, 3 static operations. And the initial comparison. So that's 4. And then we've got n times, we've got 1, 2, 3, 4, 5. We've got 5n plus 4. So here are progressions. For n is 10, we get 54. For 100, 504. For 10,000, we get 50,004. For very, very large terms, 5n becomes the dominant term, and 4 becomes negligible. If this were a million, etc., you wouldn't even notice the 4. So, analysis of algorithms is about generically predicting the resources that an algorithm may use. It can be focused on memory, bandwidth, number of logic gates, or computational time requirement. We're going to focus on computational time. And it's a very high-level analysis. So the goal is to discover a relative order among functions and algorithms. We have to understand relative rates of growth. So if we got n going from 1, 10, 100 to 10,000, etc., f of n is linear. We got 1, 10, 100. N squared goes way up fast. This is sometimes called a function of order n squared. We use the term big O when describing the relative order of functions, often referred to as big O notation. So big O of n is function of order n. Big O of n squared is a function of order n squared. Big O of log n is the function of order log n. So we also have we usually want to know the average time of the case, but average is not always clear to find. For example, sorting an average array, time typically depends on how out of order the array is. How out of order is the average unsorted array? If we can't find average, we must look at finding the worst case. The best case is seldom of interest because really we don't care. It's fast and then we're fine. So here's some complexity of different growth rates. We've got C, which is a constant. We got logarithmic growth rate. Log base 2 or I'm sorry, log squared growth rate, we've got n times log of n squared, cubic, and exponential. This last one's really bad news. In the world of analysis, there are three bigs and a little. There's big O, it's the upper bound. There's big omega, the lower bound, and big theta, it's the tight bounds. Little o is the stronger little brother of big O. Big O states the function grows no faster, where little o states the function grows strictly slower than. Big O is to little o as less than and equal is to less than. Big O is an inclusive upper bound, while little o is a strict upper bound. So the formal definition, T of n, if the function is O of f of n, if there are positive constants c and n of 0, such that T of n is less than or equal to Cf of n when n is greater than or equal to n of 0. That's called big O. Similarly, big omega is Tn is greater than or equal to. Big theta is if it's basically between the two. And little o is, for all constants, instead of using less than or equal, we use less than. So here's an example of some analysis. This is 1. This is 1. We'd say this takes 1. And this is n. And because we have an n loop here, it's O of n. So here's some general rules. For for loops, the running time of a for loop is at most the running time of the statements inside the for loop, including tests. So times the number of iterations. So here, this statement takes 1, 1, and 1. So for n equals I to 0, I to 4, the loop will run 4 times or n times, so it's O of n. Rule 2, nested loops, we analyze these from the outside in. The total runtime of a statement inside a loop is the running time of the statement multiplied by the product of the size of all the loops. So this would be n, and this would be n, so we'd get n squared. Consecutive statements, you just add up the consecutive statements. So this is n, and this is n squared, we'd get n squared plus n. Because, again, the lower term can drop out as you get much, much larger, we just call this O of n squared. If else, the running time of an if else is never more than the running time of the test plus the running time of the statements within. So, if condition, then S1 else S2, picking the larger set of statements could sometimes overestimate. Some other rules and strategies. We analyze the form from the inside out. Analyze function calls first. Reverse functions often look like loops, and they lead to something called recurrence relations. But the number of iterations here would be n, ultimately. So, here's an example. Whoops. This example would be O of n. This would be O of n squared because we got the nested loops. This would be O of n because we sum similar loops. This would be n squared. And here's some various complexities of common data structures. With the best case, worst case, and you can look this up if you like. NP-complete problems. An NP-hard problem, most problems discussed are efficient, meaning they have complexity lying in polynomial complexity. There's a set of hard problems classified NP, or non-polynomial. Complete problems are unknown whether an efficient algorithm exists, and if you find one, you find them all. They're all related. This is important because they show up more often than you think. If you know of them, we can avoid wasting time trying to find an efficient algorithm. What we typically will do is try to come up with an approximate or near optimal solution. So, for example, traveling salesman problem. Given a list of cities and the distance between each, what is the shortest possible route that visits each city exactly once and returns to the origin city? So one of the areas that this is applied is with sorting. The efficiency of data handling can often be substantially increased if the data is sorted. So, for example, to find a phone number, if it wasn't organized alphabetically, it would be rough. There's plenty of other examples I'm sure you could think of. So, how are we going to sort? Ascending or descending? The second step is how to put a set of data in order. There are a number of different ways to sort. There's lots of algorithms. Standard properties for comparing algorithms are the number of comparisons and the number of movements. To sort a set of data, the data have to be compared and moved as necessary. The comparison does not need to be exact and can be approximated with big O. The number of comparisons and the number of movements do not have to coincide. So some of these insertion, selection, quick sort, heap sort, merge sort, bubble sort, and counting sort. These all have different run times. We're going to talk about a few simple ones. So basically, with an insertion sort, we're going to find the position where the item belongs and insert it. Basically, for each element I, insert it in the proper location j such that j is less than I, and all elements greater than data of I are moved by one position. So, for I equals 1 to n minus 1, we're going to move all data elements greater than data I by one position, placing data I in its proper position. So here's an example. We start with 5, 2, 3, 8, 1. In the first iteration, we're going to move 5 towards its proper position and put 2 in its old place. In the second iteration, we're going to check 2 is less than 5, so it looks like it's in the right position. We're going to look to the next position. 3 is 5 greater than 3. Yes, so we're going to move 3. And similarly, we're going to repeat this with the fourth position because now 5 is less than 8, and so forth till we get to 1, which we're going to have to move all the way up till it is in its appropriate position, and then we are done. And here is an example of an insertion sort. So for I equals 1 to 1, and we initialize j, I is less than n. We're going to store our current data in a temporary variable for I equals I and to j, and the variable we're looking at is less than data, so b minus 1, we're going to count down. And if that's the case, we're going to move our data and restore the original value into the next position. And that switches it. And it's literally this simple. I would recommend stepping through this algorithm. Selection sort and insertion sort, we will bubble sort, I will most likely create examples for you to build during homework.